Hi, I want to talk about definite integration in the realm of u-substitution with you in relationship to this problem right here. So definite integration is just definite integration. Fundamental theorem of calculus tells me I need to find an antiderivative and evaluate it at these two places and take the difference of those two values. Okay, fine. So in some sense, you don't need this video. If you can use substitute and you can do definite integration, then you can totally do definite integration with u-substitution. But I want to talk about some finer points in terms of doing this, some risks and easy mistakes to make that I see people make. I'll try to point those out as I go through this and collect them into a sidebar of advice. Okay. So in some sense, the first thing that we've got to do is just like do the integral. Like we just got to like find the antiderivative and then we'll deal with the definite part of it. So I feel like step one is to do the integration. Okay. So let's go ahead and do that. I think that u should be the thing inside. And we're going to take the derivative of it and then hopefully see its derivative or a scaled factor of it somewhere on the outside. I see stuff inside of a sign, and so I'm going to let that be my u. So I'm going to let the stuff inside of here be my u. So I'm going to let u equal to pi times x cubed plus 2, which means that du is equal to 3 times pi times x squared dx. So I just take the derivative and then I attach a dx of it onto the outside. So I've got the pi x squared part. I'm missing the 3. So let's multiply by 3 to get that, like that. And then let's hopefully find the rest of this taken up in terms of u. So that part right there is all going to be du. That part right there is u. And so now I get to rewrite my problem in terms of u. And this is where my first risk point is going to be. So the integral of, let's see here, sine of u du, and it's so tempting to want to write just plain 0 and 1 right here. And it's not wrong to do so, except that these are in terms of x's, and these are still in terms of x's, but my integrand is now in terms of u. So my first bit of advice is I think you should immediately attach the like x equals to the upper and lower bounds. So this part right here and that part right there. So what I mean by that is I really want to attach x equals, x equals, x equals, x equals, because that's the super strong visual reminder that I'm in terms of x, I'm in terms of x. And in fact, if I just had 0, 1 here, I'm almost certainly wrong. Because if I don't name the variable, then we're assuming that these bounds go with this variable, and there's practically no way that that 1 and 0 map to 1 and 0 as we pass through u. Okay. So we have a couple of options at this point. And so I think that we need to as a next step, we need to either unsub back to x and evaluate, or I think we need to change the bounds of integration from x to u. I'm going to do this problem both ways, and we'll examine which one is easier, knowing that for some problems it's probably easier to do one, and for other problems it might be easier to do the other. I think it might generally be easier to change the bounds of integration, but let's see what happens as we do both. Okay, So let's go ahead and do the integration now. We haven't quite gone the step to find the integrand. So this is equal to a third of, with a minus sign of cosine of u, but u evaluated from x equals 0 to x equals 1. So one of the options that I have is to unsub and evaluate. So let's do that. So I have minus a third of cosine of u evaluated from x equals 0 to x equals 1. X's, u's, conflict, can't substitute them in. So that's equal to minus a third of cosine of pi times x cubed plus 2 evaluated from, and now I can write 0 to 1 because I'm back in terms of x's, but I think it causes no harm to keep writing my x's. So I'm going to keep writing them. So this is equal to minus a third of, whenever I have factors like this on the outside, I like to just like group it like this so that I don't have to have the minus a third on the inside. I think that generally helps me stay on the right track. Cosine of pi plus 2 minus cosine of 0, so 2. And I probably could do something with like the shift of these to simplify it, but I think I'm not going to worry about that right now because I think that's going to be a sidetrack. Instead, I think what I want to do is try the other thing where I change the bounds of integration and I should get the exact same expression. So what do I mean by change the bounds of integration? I want to rewrite that this is equal to minus a third of cosine of u evaluated from u equals to u equals, so that I don't have to like unsubstitute. And I'm going to get the same number no matter which way I do it, assuming I do it correctly. So here's how we do that. So when x equals 1, we need to figure out what u of 1 is equal to. So here's u of x, right? So we need to pass this bound through this function to figure out what u of 1 is equal to. That's pi plus 2. U of 0 is equal to 2. So by taking these values and feeding them through my u function and finding out what they map to, I now get to put these expressions right here, pi plus 2 and 2. And now I can evaluate this expression, and that's equal to minus a third of cosine of pi plus 2 minus cosine of 2. Oh, and I got the same thing. Yay. That's great. So I guess my advice there is to like get comfortable with both of them because they're both useful. This one here doesn't require necessarily explicitly mapping x through u, except you always have to do it at some point when you do the evaluation. Or you can do this and take the bounds in terms of x, pass them through the u transformation, and then see where they map to and put those up right here. And I think one of the keys to success is to immediately attach x equals to these bounds of integration because it's so easy to forget along the way that these are x's, that the 0 and 1 are x's, and that the 2 and pi plus 2 are u's. If we don't attach those, then as soon as we get to this part right here, we're going to do this. We'll have 0 and 1 right there, and we're totally going to get the wrong answer. So I guess my biggest advice for doing definite integration with u-substitution is to have the name of the variable attached to the bounds of integration right from the beginning, and at every single step, every time you write what that integral is equal to as you work through the problem. I do hope this advice serves you well, and I will see you again next time for another video. Thank you. Bye.